All right, greetings from the lovely city of Cincinnati. Miss you guys, I really do. But never fear, I can use my magic surface to continue to reach out to you guys and try to push it through a last little bit of chemistry. So this is your second to last lecture of the school year. And I know you guys are going to be sad, but never fear, you can always go back and rewatch all the lectures from this year anytime you want because they're still there on YouTube. Alright, so far in this unit, we talked about what equilibrium means in terms of forward and reverse reaction rates and in terms of concentration of reactants and the products. And of course, you're remembering that equilibrium does not necessarily mean equal concentration. You've also learned to make some calculations to determine an equilibrium constant. And in order to do that, of course, you need to be given the initial concentrations and at least one equilibrium concentration. All right. And likewise, which was a little bit more math intensive for us, we learned to make calculations to determine the equilibrium concentrations. But in that case, you need to be given initial concentration again and equilibrium constant. All right. So just a quick refresher there, right? If we're given initial concentrations and at least one equilibrium concentration, we can calculate that equilibrium constant, right? If we're given the initial concentration and a constant, we can calculate equilibrium concentrations. All right, so you just need to look at what you're given and then work through the steps. All right, but moving into some new stuff, we're going to talk about this new principle of what we call the reaction quotient. All right, and that reaction quotient is a new little term for us, and it's related to our equilibrium constant. So let's go back. Let's do our favorite little reaction here, imaginary reaction, where we have reactants over here on the left-hand side. We got our products on the right-hand side, right? So the A and the B would be our reactants, C and D would be our products, and the little letters there, of course, are our coefficients. Okay, and so we've already learned that our equilibrium constant expression looks like this, right? So I put the little C next to K now because I did mention in class the other day that we're talking about equilibrium in terms of concentration. Okay, and so notice we have our reactants, our product reactants on the bottom and our products on top, and then our little coefficient letters there become our exponent, right? So that is stuff you already know. All right. So our reaction quotient is found exactly the same way, right? So, but notice in this case I changed the Kc to Qc. So the symbol for reaction quotient in terms of concentration is Q. All right. But it is calculated exactly the same way. And so you might be wondering, well, Mr. Huderberg, why are we learning a new name for something that has the exact same calculation? Now, I said it's calculated in the same way. All right, there is a key distinction you need to make between our equilibrium constant and our reaction quotient. Okay, so as you know, our equilibrium constant, the molarity is referring to the molarity of the reactants and products at equilibrium. So once equilibrium has been achieved and our forward and reverse reactions are occurring at the same rate and there's no net change in their concentration, that is how we can calculate our molarity, our equilibrium constant. We can't do it unless we're not at equilibrium. Now, reaction quotient doesn't have to occur at the equilibrium point. All right, so the reaction quotient is calculated any point in the reaction. Okay, so let's say, for example, that I have a long reaction that maybe takes several minutes or several hours to occur, and I measure the molarity before equilibrium has been achieved, right? I should be able to get a quotient and relate that quotient to equilibrium. Or if I want to know whether equilibrium has been achieved, I can use that quotient and compare it to my equilibrium constant to decide, I need more product to be formed before our reaction has reached equilibrium. Okay? So, why would anybody care about the reaction quotient? Okay? More importantly, why would a chemist care about the reaction quotient? Well, I'll tell you why. So again, going back to that situation where I have a reaction that maybe takes some time to complete. All right, I can measure the progress of that reaction by relating the reaction quotient to our equilibrium constant. Okay, and so there's a few things I want you to know. So first of all, being able to calculate that reaction quotient, piece of cake for you guys. You guys know how to do that already. Just plug and chug the numbers in. Okay, here's what I want you to know though. If a reaction quotient is less than equilibrium constant, then I know that I'm going to continue creating more products before equilibrium is reached. If my reaction quotient and equilibrium constant are the same number, then I know that the reaction is at equilibrium. And if, perchance, the reaction quotient is greater than the equilibrium constant, that means I'm going to shift back to create more reactants. Now, why would that happen in a reaction? Why would I cause that reaction to shift back? What would cause it to proceed farther than it normally would? We will get to that at a later date when you guys learn more about what's called the Chatelier's principle, which I'll get to you guys on in just a couple days, probably 2 days from the time in which you watch this. All right. So you're going to do the ChemQuest, work through reaction quotient. I don't think you guys are going to have any trouble whatsoever with that. These are the three things you need to remember, though, right? If QC is less than KC, we're going to get more products. If QC equals KC, we're at equilibrium. If QC is greater than KC, we're going to get more reactants. All right, that's the thing there. Calculation for doing that looks like that, just like that equilibrium constant. Okay, you just have to understand that the equilibrium constant can only be calculated at equilibrium. Reaction quotient can be calculated at any time. All we need to know is the relative molarities of our reactants to our products. All right? Peace.